Yep. And the sound is, yes. Okay. Is everybody here? Maybe not in the room, but is everybody here? It's getting a lot. You should have been 16 here, but okay. That's why we have the video, I guess. So everybody here has access. That's good. The information now is not entirely up to date. I believe we are here on Wednesdays. It's going to be permanent, I think. But on Thursdays, it might differ. Most of the time we will have Kjell number 4, which is an okay room. If not, then we have to be here. But normally Kjell number 4. I think I got it most of the weeks. You have been given some material. You have been given a compendium. I'm going to have a peek into that one today, and also you have been given the Strouhal program, which is roughly where we left off the last time. And so we went through the projection method algorithm inside the Strouhal algorithm. And what we are going to do today is continuing a little bit with just a case, so you can see how this Strouhal number enters and why we actually are using the Strouhal number. The case, which actually you should be able to program yourself, you have the MATLAB code, is sending in a constant flow and hitting sort of a rectangular object here, and then a choice of proper Reynolds number. You should get this nice von Karman vortices alternating shedding from this blunt object. The way the Strouhal program has been made in MATLAB, you have a length scale of 1 no matter what you do, and the reference velocity is 1. So you shouldn't push in more than 1 here, because the only parameter you insert into the code is the Reynolds number. Hence, the number you are inserting is Reynolds number based on the width, which then should be fairly big to have a decent Reynolds number in the range, some hundreds, around this length scale here. So you see the number that I've chosen here. And the problem now will be, we have knowledge, we have a suspicion that Mother Nature is going to set up this oscillatory motion. We don't know the frequency. Well, actually you could find it, but let's assume that we don't know it. Then what is my time scale in the problem? We have no idea. So how can we actually find it? Well, you really have no option, because this time scale is sort of unknown, built into the Mother Nature. Hence, we have to find it. So we really have no other choice than create this sort of a dummy default time scale, length by velocity, setting the Strouhal number to be 1. And then Reynolds number is the only parameter into the problem. And then play around with delta t's and hope that we don't skip the entire dynamics entirely. That's the danger. I mean, if you have a fairly big delta t, then you might overrule the dynamics in the problem. So you have to be careful when you don't know this time frequency. So here we are searching for it. The boundary conditions into the Strouhal algorithm. Here I have 2 walls, but I'm not interested actually in a channel flow here, so I say these are slip walls. So I use a slip condition here. Of course, the velocity in the y direction is 0. They're solid walls in that respect, but not in the streamwise direction. So I just set the velocity, the ghost cell down here, equal to the one inside, and same above here. Inlet, that's easy. You just say x velocity is 1, y velocity, you set him to be 0. And the outlet, both Neumann conditions, derivative equal to 0. So that is the state. Initially then, we start with everything equal to 0, which might be a bad idea, because we are going to search for a laminar solution here, which is time dependent, and it might take some time to sort of establish it. So if you have a completely symmetric setup here, this block is in the center, everything is symmetric around this line, then you risk getting a symmetric solution, which is actually also a solution to the Navier-Stokes. It's just unstable. So it would actually be better if you have this one a little bit, maybe one cell down, so you have some asymmetric problem. Then he will start the shedding faster. Normally, if you run a long time, he will manage to get enough errors to sort of see that it's not symmetric anymore, and then start with the shedding. But to help him, you could make it a little bit asymmetric. You could also play around with this execute file, the Sola Windows version, and play around there to see how it can start easily. That one is much faster, of course, than this MATLAB script. So here I have run, after 10 time units, the situation looks something like this. You start getting the wavy pattern, which then will be time dependent on the back of this block. Here you have something suspicious in the front. This is sort of a hint. You should use more cells when you get this quite clearly an unphysical behavior. So this is not good. Here I really don't care if I do something wrong here and if I do something wrong here. I'm interested in sort of the dynamics or just around the block, so I don't care. But you see for yourself, I have only 4 cells here and 2 cells here, so it's fairly small. I should have had a lot of more cells here. But as an illustration, it's okay. So the resolution here is quite poor. So then you have an option then how to plot your results. Here streamlines, here isobars, and yes, as time goes by they have a sort of a changing pattern. Here you see the streamlines again indicating not so well resolved here in front, but okay. The isobars, you will have low pressures inside these alternating vortices, of course. So the question now, how to find this frequency? How to find the frequency? Yes, you could have made a lot of these different plots and then see when can you find this picture repeating itself, and then take the time difference, or this picture. So I try to do that. You have, here is the beginning, time equals 10, and then you see he's evolving, printed out for every 0.05 time unit, and to get it back to this one, well then actually you have to go all the way up to 0.65. So one period in my simulation is a time unit of 0.65, around there roughly. Then I have the sort of the same pattern that I started with, somewhere in between here, I think. You can do the same there with the pressure, the isobars. When do you get this image again? So that's the starting image. You have these two here, the major one here, and that's time equals 10, and then the end time here, more or less 65, I would say, or again somewhere in between here. So yes, that's possible. That's one way to do it. It's not the best one, but yeah, it's possible. A better one would then be, instead of wasting time with all these plots, you calculate inside your program, you calculate the lift and the drag force for on the block, say lift and drag. So here you have the block, and it was 2 by 4 cells. The minimum block size has to be 2 because you're using the velocities inside the block as boundary conditions. So let's look at the drag first. How to find the drag force? Well, it's going to be an integral of the pressure and an integral of the wall shear stress. But the areas there will be different. So numerically, how are you going to do this? The pressure, they are located in the cell centers. So here you have pressures to the left and here to the right. So to find this one, you have to do something like this. You take the sum of, say, pressure left, pressure right, and you just take the difference, pressure left minus pressure right, multiplied with the phase that they are attacking, delta y in this case, xy. And yes, you have 4 of these. Then you should have the net pressure force acting on this one. Plus, and then we are going to need what? The wall shear stress. How can we find that one? Well, we have here in the live mesh system outside, you will have the streamwise velocity entering here in the mid of these cell faces, the delta y's. On the center we have location of our streamwise velocity. Same goes down here, like that. Inside I use boundary conditions, so I get 0 velocity here on the wall. So I construct a velocity here so that on average we find 0. Like that. The corners I have to treat specially, so don't mind that. So that means we need to find the forces here. That should then be the viscosity, and then you need the velocity gradient, which then you simplify by saying the velocity outside u divided by delta y half. And then you sum all of these, but they are acting on a face which then should be some delta x, something like that. Of course, here you might want to do an interpolation, finding the velocity at this point, and you have 0 down here, and then he will act here. He will act on just this delta x, and same average here, and he will work on this one to get it more precise. And then you of course do the same down here. So the friction forces acting on the top and the bottom. And then you do the same, but now you just flip it. So now you will have the lift force, which then will be sort of identical but flipped 90 degrees. Then you will look at the pressure in the y direction, different pressure difference here, and then the flow acting in this direction. And then you plot these two forces acting on the block as a function of time. Easy calculation to get these numbers for every time step. Then you will have it much more accurate than looking at a lot of different plots. Any question to this one? You don't need the detail correctly here, just so you get the idea how this can be done. That's good. What you get then is something like this. So here you have the lift force for every time step, and you just look, okay, how long is one period. So you start here, and then you find him roughly here, 0.6 something small. So of course much more accurate. Here also you might argue, isn't my delta t a little bit big? A lot of things is happening from one time step to the next, so maybe I should have had even a smaller delta t than the one I had to get it more precise. Yeah, that might be true. I think I found, well, I don't think I have a picture of it. No, I don't. If you had plotted this one all the way from time equals 0, this lift force, he would have started as 0. And then he will slowly start, and then finally he should be established. So you have to simulate long enough so that this one sort of is constant periodic from here on, or else you're not it's not a steady state, say a steady motion then, so that the amplitude is sort of constant. Then you have a steady situation for these vortices. If you had plotted the drag force, he would be twice as fast. Frequency will be doubled. Remember, the lift force, he will turn alternately up and down, but the drag, he will go the same way. So he will be twice as fast. Anyway, when I calculated the Reynolds number, the Strouhal number here, on this calculation, I think I got, what was it? I got 0.19. And the correct answer is 0.17. So I missed a little bit. But I mean, you can see for yourself, quite crude delta t, and also you saw the resolution was quite crude. So yes, but it should be possible to hit it quite nicely with a good resolution. And then comes the point with the Strouhal number. If we had known this in advance, then we could have done a much better, be more confident with our simulation. So let's write it here. Strouhal number. If it is known, if SC is known, it's only a time scale actually, but then you should use it to be able to choose a proper time step, resolving the dynamics in the problem. So that is the argument for using a Strouhal number. I mean, normally when you are provided a partial differential equation and your task is to solve it, and you have no idea what the solution looks like, what do? You write the equation on a non-dimensional form. You scale it so that all your unknowns should vary between 0 and 1. Should be around unity. All parameters or all input parameters you just set equal to 1 if you have any constants like viscosity or whatever. Then you know that the time scale should be around 1. That's sort of given when everything is non-dimensionalized. But the Strouhal number, I mean, it's born, this dynamics is born from the nonlinearities in the Navier-Stokes. So this built-in frequency from Mother Nature, we have actually really no idea. But if we had an idea, if we could sort of look up the Strouhal number in advance, then we know what time scale these motions actually is performing about, how long time they take, and then we can better choose a nice delta t that can resolve this motion. I mean, if you're unfortunate here, if you choose a time step bigger than 1 period, you don't see it at all. It will be filtered away. Using an implicit code, for instance, you could have chosen a very big delta t and then nothing will happen. Or if something is going to happen, then it's going to be dead wrong. So resolving the dynamics, that's the whole point here. Okay, that was the sort of the motivation for using a Strouhal number. It's not that widely used, but you'll find a lot of references to the frequency, finding the Strouhal number for flow around cylinders, flow around blunt objects. No problem there. So they should be easily found. So then you might argue you don't have to rewrite the Navier-Stokes to get them on a non-dimensional form. If you know the Strouhal number, then you can of course find the time scale in seconds, and then you can choose a proper delta t in seconds if necessary for one particular problem. So that's okay. Tending to something else completely. We are looking now into the world of stability. If you look at the MATLAB code, you have a control, a test for your choice of delta t there. Let's see if we can find it here. Yeah, I think it was here last year. Yeah. Sorry, you don't see anything. Here's the beginning of the Strouhal code. You choose the time step, you choose the Reynolds number, and you choose how many cells you want, and you get the delta x and delta y equals h. Then you have an if sentence. Delta t, if it's bigger than the smallest of these three expressions, then you get a warning. Delta t should be smaller. So here you have the stability criteria, and we have three of them. Where do they come from? That is the task. Find them. Dealing with stability. In numerics, here you have two classical methods. One is matrix methods. You set up your problem on a matrix form. So you have a coefficient matrix, a huge one, which then you have to analyze, finding the eigenvectors, eigenvalues, and then you have some numerical theorems there. Gershgorin, Bauer, several of these guys have then a lot of theory behind this analysis to find a stable solution algorithm. Can be complex, and you can imagine for yourself to set up an equation system on a matrix form. Your equations has to be linear. You have no choice. Too bad. They're not linear. You have to cheat, you have to linearize. But that actually goes with any method. So this is one method. Another famous one for Neumann. That is using Fourier. So you say the anode goes or can be expressed as a Fourier series, and then you take one arbitrary wavelength and see how that anode either decrease or increase depending on the choice of delta t. So that's the two most famous, and I'm going to show this one a little bit how it works, and this one I'll talk a little bit about it, but we are not going to use either of these. These are the standard methods in any numerical course. I guess you have heard about them before. So I'm not going to go into any details of these, but you should be, of course, aware of them. Here, I'm going to teach you a quick and dirty way to do this. It's really doesn't have a name. I call it the max-mean method. Some call it the method with positive coefficients. It's a very simple method, but it's quite crude. And in some problems, it really can't give you the correct answer. And even some problems, it can't give you any answer, not even the wrong ones. So it's not a reliable method. These will be much more accurate. Although either method, you have to linearize your equation. It has to be a linear equation system, or else you can't do either of these methods. And if you want to use a finite volume code, finite element, spectral codes, whatever code, you have to go back to finite difference, sort of transform your equation system into finite differences to even do the analysis. Not so easy to do directly. Well, it's possible, of course, to set up equation systems with integral methods, but not easy. So normally, most of this analysis is done with finite differences. And just so that you are not confused here, this is for parabolic and hyperbolic equations, not for elliptical equations. Why? Well, elliptic equations, if you can recall the demand for boundary conditions there, you have a region in space, you want to solve it, you absolutely have to provide him with boundary conditions all around the domain, on the entire boundary. That was the demand for an elliptic, to obtain an elliptic solution. You need boundary conditions all around. Here you don't have any marching direction where you could march the solution forward in either time or space. That is only parabolic and hyperbolic problems. So elliptic problems, we actually don't have any stability issues at all, except when you want to solve an elliptic problem. We saw that when you use these traditional iterative methods, Jacobi, Gauss-Seidel, SOR, then we might run into numerical instability. But that is a different stability than we're talking here. So elliptic, say they can be troubled with, say, call it iterative stability. That is actually, in practice, a nasty problem. If you choose an iterative method, okay, then you have to be careful, do it properly so that it doesn't explode. So it's not numerical stability, it's just an, well, numerical stability. We should have a different name for that one as well. Stability. Stability and iterative stability, that's okay. Everybody with me on this? There are two quite separate things. That's good. So how do we deal with stability? For stability, we differ between necessary versus sufficient. Finding the necessary stability criteria versus finding the sufficient criteria. So say roughly the sufficient criteria, that is precisely, exactly the stable limit. So this one is the precise one. Precise. This one, the necessary criteria, if you find a necessary criteria, it might be too restrict, too crude. So this is a little bit rough, too crude. It might be the same, that depends on the method. So we'll come back to that later. So like these methods here, if they work and you have a linear equation system, they will typically be able to provide you with an exact correct delta T limit. Quite precise. This method, he will typically only be able to give you a crude criteria. You would be dead certain that it's stable if you use it, but it might even be stable if you chose a bigger delta T. If you violate this criteria, it could still be stable. You really don't know. So, of course, we would like to have the correct one, the sufficient one, but might be too hard to find it, even impossible. So then maybe we have to be satisfied by choosing or just finding the necessary criteria. How to solve, how to find our stability criteria for the entire Navier-Stokes. That is our aim. So my problem, Navier-Stokes, and here I just write it in the I component. We have the time derivative, and then we have some convective terms, ui dxj, and we have a pressure term in the I direction, and then we have viscosity, double derivative with respect to all variables. There you have the entire Navier-Stokes. Now for complex partial differential equations such as this one, you don't try to find the stability limits here all in at once. It's too complex. So typically what you do, you look at only certain terms at a time. You simplify it. Look at only certain terms. at a time. And also, sadly, we have to linearize. So what are we going to do? Well, we start with looking at these two terms. That is then the advection equation. So we start here, only these two terms, advection. And that one is actually a hyperbolic equation. Now it's just a first order equation. Sadly, it's nonlinear. Here you have unknown multiplied with the derivative of the unknown. So we have to linearize this one. So here we cheat, inventing a constant velocity here. So that will be the first equation we are going to look at. Later we will look at time derivative and the last term. Then we are talking diffusion. And that one is parabolic. Also, we will have a peek into a steady problem here. I need some more space. Taking the advection term and the diffusion term. So then we are using, say, a diffusion advection equation. But it's a steady state equation, so not parabolic, not hyperbolic. So it will be actually of an elliptic nature. You have to specify him with boundary conditions all around. And also we will have a peek into solving or looking at the entire Navier-Stokes directly. It's actually possible. You can get some information out of it. But this is typically how you have to deal with complex partial differential equations. Look at only certain terms at a time. And yes, we are going to achieve the different stability limits sort of step by step here. So that is the layout for the next couple of lectures. Any questions so far?
I was just thinking, for me it sounds like it should be opposite with the necessary and the sufficient.
Yeah, well, they're just names actually. Yeah. So yeah, no, but this is how they have defined it. So sufficient is just sufficient, just precise, exactly what you need to have the stability. This is a necessary, so you have to set a delta t, but it might be too crude. I can sort of agree with you that the logic might be switched here, but yeah, it's just names. So just be aware. Some of these methods may provide you with the exact one, but simple methods might provide you with something that is not quite accurate. And here, since we know that the entire equation system is nonlinear, you can't really get the precise one either way. So you might risk that the delta t criteria you find, the problem might be stable if you choose a smaller one. and the problem might be unstable even though you are inside the limit. So if you play around with this Strouhal code in MATLAB, changing the Reynolds number and then changing the delta t, you will find exactly that. So it might run even though you have a too big delta t. It might explode although you have delta t within the criteria. So they are not exact, no. Other questions? Then we take a break.